Right. Right. Mm. Okay. So now we'll go to the some heat practicals. We'll go to some heat practicals. So practical number, I think practical number 23. I think it is practical number. Mm, mm, it's practical number 20. Four. So now to practical number 22 and 23 removed from the practical list. So we have to discuss practical number 24. Practical number 24. Practical number 24. Practical number 24. Okay. So write down what is practical number 24. Write down to verify the relationship between pressure and the absolute temperature. Pressure and the absolute temperature of a gas at constant volume. Of a gas at constant volume. Now we can remember ideal gas equation. Ideal gas equation PV equals nRT. Verify the relationship between pressure and the absolute temperature. Absolute temperature means temperature measured in kelvins. Then constant volume. So we are going to obtain a relationship between pressure and the absolute temperature while maintaining volume constant. For a certain amount of gas, simple N is a constant, R is a constant. What type of relationship between pressure and absolute temperature when you maintain volume constant? If you maintain volume constant and mass of that gas sample is constant, then we can tell that pressure is directly proportional to absolute temperature. When absolute temperature increases, pressure of the gas increases. When absolute temperature decreases, pressure of the gas decreases. Okay. So what we do here we the materials and apparatus. Materials and apparatus. Uh, write down. Write down. Okay. Give me a second. Okay. So materials and apparatus, write down, write down constant volume gas thermometer. Number one, constant volume gas thermometer. Right. So then beaker of water, Bunsen burner, Bunsen burner, tripod, a tripod. Next one, a tripod, a wire gauge, a wire gauge, a stand and a stirrer. A stand and a stirrer. Stirrer means that STIRRER. A stand and a stirrer. So and also mercury thermometer. Okay, we need mercury thermometer as well. Mercury thermometer as well. Okay, right. So then quickly start draw this diagram. Start drawing this diagram. Okay. So you guys also keep on drawing, then you can remember the apparatus and what are the components required for this practical. Okay. So I explain what's happening, why do we use each component. I will explain detailedly. So you don't need to worry or make any fear about that. Keep on drawing. Keep on drawing. There is a scale to measure the length. The kind of scale is there. Keep on drawing with me. Keep on drawing with me. Now, this is a flexi hose tube, and this is kind of glass tube, and this glass tube is open to atmosphere. So therefore, atmospheric pressure is acting on the surface of the liquid. Okay, fine. Atmospheric pressure is acting. So this point I marked as point capital C. This point is point capital D. Point capital D. This is a scale to obtain the length. kind of meter ruler or something, kind of scale to measure the lengths and heights. And this is a water beaker. Water contains in the beaker, right? So when you're talking about this container, if not this spherical container, this spherical container contains the gas. So what is our ultimate goal? We want to obtain what is the exact relationship between pressure of a gas and absolute temperature of the gas. So you can select any gas. You can select nitrogen as your gas. If not, you can insert oxygen. No, you can insert air inside this bulb. So you can consider any gas. We have to assume those gases as ideal gases. That is one point. So then, according to that ideal gas equation, we know what type of relationship between gas pressure and absolute temperature. There is kind of direct proportionality between pressure and the absolute temperature, but we are going to prove that. We are going to show this experimentally. So we are filling a gas that you desired in this spherical bulb. So then understand that gas is, we are assuming mainly that gas that you are inserting is only filled in this bulb, but as this bulb is connected to this connecting rod, as this bulb is connected to this connecting tube, we want to assume that gas is occupying this volume as well. Until here, that gas is occupied this volume also. We are actually, when you insert the gas, that gas spreads throughout this connecting tube until this liquid level. But when we are doing this practical, when you do the calculation, we have to assume that gas is only contained in this bulb. So you understand that later. So therefore, now this is kind of connecting tubes. Generally, we maintain this tube very thin. So therefore, we are using capillary tubes as the connecting tubes. So therefore, remember this tube is capillary tube. If I ask you in an experiment, if they ask you why it should be capillary tube, I told you we are assuming entire gas is filled in this bulb only. But what happens due to this connecting tube, some amount of gas will be occupied this space also, right? So then why we are using capillary tube as the connecting tube? We know capillary tube volume is very small. Even though this gas spreads in this capillary tube, this region, when you compare with the bulb volume, we can neglect the volume of that gas in these capillary tubes. Why? Capillary tubes are very small tubes. The volume of the capillary tube is very small. Therefore, gas inside this capillary tube is, we can neglect when you compare the volume of the bulb. When you compare the volume of the gas in the bulb, we can neglect volume of the gas in this capillary tube. Why? Capillary tubes are very thin tubes. That's why we are using this as capillary tubes. You also write down capillary tube. Capillary tube is capillary tube. Capillary tube. Okay. All right. Then, okay. Then what? So now there is a stirrer. I don't know how to pronounce them. There is a stirrer. We know we use stirrer to mix the water. And there is a thermometer as well, mercury thermometer. There is a mercury thermometer as well. Mercury thermometer. This is the mercury thermometer. So you also mark the mercury thermometer. This one is stirrer. Stirrer. And this is your that tripod, right? If this is your stand, this is your Bunsen burner, right? Tripod stand. This is your Bunsen burner. This is water beaker. water beaker. So this is your Bunsen burner. Bunsen burner. So this is the stand, if not the tripod something. Stand, if not tripod something. Okay, right. So then now what is this? What is setup? Still you are not very familiar with the setup. So far everything is fine, raise your hands. So far everything is fine, raise your hands. If you understand everything so far, just raise your hands. Okay, right. So this is the bulb. Bulb. So I mark the gas as black color dotted dots. The gas is black color dots. Whatever the gas that you insert in the bulb spreads through the capillary tube as well. Spread through the capillary tube as well until it's liquid. Then you might ask, what is this setup? This setup is what? This setup is the manometer. Right? You guys know what is manometer. This setup is the manometer. 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 Okay. Right. Okay. Manometer. So there is a indicator. So there is a indicator. There is a indicator. I just mark this indicator like this. That's an indicator. And I will explain. I will explain detailedly everything. This liquid is mercury. This liquid is mercury. This liquid is mercury, right? This liquid is mercury. If I say it can be mercury or it can be water, okay? It can be mercury as well as it can be water also, right? Okay, some kind of liquid. I say density of this liquid is rho. Density of the liquid inside this flexi hose with these glass tubes, density of the liquid is rho. If I ask you, what is the pressure? What is the pressure? What is the total pressure at this point? The total pressure at this point will be, if you know this height, simple H height. If you want to find the total pressure at this point, and if you know the height from that point to the free liquid surface, simple H, what is the total pressure at this point? Total pressure at this point will be H rho G plus phi. Am I correct? H rho G plus phi. Okay. Then if I ask you, what is the pressure at this point? Now you can understand these 2 points are at the same horizontal level. Then if I ask you what is the pressure at this point, the pressure at this point also should be the same pressure as this pressure. At this pressure. Okay, this pressure. Keep in your mind. Okay. Right. Okay. So now what we do, write down. Just write down. Just write down a method. Under methods, write down. After immersing the bulb in water, after immersing the bulb in water, after immersing the bulb in water, comma, arrange the tube AB. Arrange the tube AB. Arrange the tube AB. Always see what is AB. Oh God. Arrange the tube AB. So what is AB tube? So this is your AB tube. Arrange the tube AB so that the mercury meniscus in CD, so that the mercury meniscus in CD, so that the mercury meniscus in CD, so that the mercury meniscus in CD. So sorry, this point should be B. Okay, I made a mistake. This point should be B. Okay, this point should be D. I made a mistake. This point should be D. Then this is A. So what I told you under methods, after immersing the bulb in water, arrange the tube AB so that the mercury meniscus in CD touches the index tip. Touches the index tip. So I told you now this tube is filled with mercury. So what you want to do is, after you immerse this bulb in the water, right? Out of the bulb, water is there. Inside the bulb, gas is inside the bulb. Until here. Beyond this common interface, there is mercury. Water outside the bulb. Inside the bulb, there is gas and gas. Throughout the capillary tube also, there is a gas until this common interface. Below this common interface, there is mercury until here. Then again, air. So what they are telling, you want to arrange tube AB. What is my tube AB? This is the tube AB. Arrange tube AB so that the mercury meniscus in CD. So this is the mercury meniscus in CD touches the index tip. So there is an index tip here. You want to always make your mercury meniscus in CD tube touches with the index tip. So then how you do that actually? Now you are able to move this tube AB up and down. So while moving tube, when you are carrying out this practical, while moving your tube AB up or down, always you want to ensure mercury meniscus in CD align with this index tip, align with this indicator. So why we are doing this, I will tell you. Now you understand basically what are we going to do? We are going to show the relationship between pressure and temperature. So what, while maintaining volume constant. So then if you have a right understanding about this equation, what are we going to the practical? We are going to change the temperature by using this Bunsen burner. So when you burn Bunsen burner, what would happen? Heat is propagating and water boils. As this bulb is inside the water, the gas inside the bulb, the gas inside the bulb gets heated. As a result, temperature of the gas increases. So this is your gas sample. Your gas sample is inside the bulb. What are we going to do for this gas sample? We are changing the temperature of the gas sample. By changing the temperature, what we are going to observe? We are going to observe the pressure. Right? So you are going to change the temperature. Okay. By using the burner, you can change the temperature. But how are you going to measure the temperature? You have a thermometer also. Right? You have a thermometer inside the water. So you can measure the temperature of the gas using the thermometer. There are some points to be discussed at that point. I will tell you later. Right? Yeah, there is a gas sample. You are going to change the temperature of the gas sample. How are you going to change the temperature? By using the Bunsen burner, you can heat the gas sample. Okay, you can change the temperature, I understand. But how are you going to measure the temperature? Use the thermometer. Use the thermometer, you can measure the temperature also. So when temperature changes, when temperature increases, what should happen for the pressure if you maintain volume constant? If you maintain volume constant, what should happen for the pressure? Pressure should definitely increase. The problem is, you should argue, how am I going to maintain volume of the gas constant? Now, then you want to check first, what is the volume occupied by the gas? So gas is inside the bulb, gas is inside the capillary tube until here. So at every temperature, You continuously increase the temperature. At every temperature that you are going to take readings, you want to maintain constant volume. You have a understanding now what would happen with the time. Now you are heating the gas, then what would happen if you don't maintain volume constant? When you keep on heating the gas, what should happen? What should happen? This gas, this gas volume expands, right? This gas volume expands, and what would happen for this mercury meniscus? This mercury meniscus tries to come down. When this mercury meniscus comes down, when you continuously increase your temperature, what would happen for the gas volume? Gas volume increases. But we should carry out this practical while maintaining constant gas volume. Then how do you ensure constant gas volume for any temperature? Always, if you can maintain your mercury meniscus exactly at this indicator tip level, always. Yes, obviously this gas tries to go down by pushing this by pushing this mercury liquid. Obviously gas tries to go down, but if you can manually adjust AB tube up or down, if you can manually adjust AB tube up or down, and if you can always maintain mercury meniscus at this indicator level, we can ensure same volume of gas is inside this setup. Forget about the expansion. Forget about the expansion of bulb, and forget about the expansion of capillary tube expansion. Then that's why now then if someone asks why are we moving AB tube up or down, to always ensure throughout the practical volume of the gas constant, to maintain volume of the gas remain constant throughout the practical only. We are changing AB tube up and down, and we are always keeping mercury meniscus at this indicator level. Then we can ensure same volume or constant volume. Then okay, right? I understood how to increase the temperature. I understood how to measure the temperature. I know how to maintain volume of the gas constant. Now I learned. But the problem is when I increase the temperature while maintaining volume constant, pressure increasing. So I understand pressure should increase obviously, but how do I measure that pressure? How can I measure that pressure of the gas? That is the problem. How can I measure the pressure of the gas? Using this manometer. Right? Using this manometer. What will happen? Let's say at a certain temperature, you want to measure the pressure of the gas. We know that at a certain temperature, pressure at any point on the gas is same. At a certain temperature, pressure at any point on the gas is same. I say pressure of the gas is capital P for an example. What is the pressure at point D? Pressure at point D also capital P. Because same gas is spread throughout this region and pressure of gas at any point is same, pressure at this point D also capital P. So then you can tell that pressure that capital P equals to as point D and this point are in same horizontal level, pressure at point D, that means capital P equals to H rho G plus 5. H rho G plus 5. Hands up to now, everything is very clear. Hands up to now, everything is very clear. Hands up. If you understand everything, raise your hands. Okay, right. Okay, now first point we wrote AB so that the mercury meniscus in CD touches the index tip. Next point, note the reading of the indicator tip. Note the reading of the indicator tip, comma. Note the reading of the indicator tip, comma. So you want to note down the reading of the indicator tip, comma. The reading of the mercury meniscus in AB. The reading of the mercury meniscus in AB. The reading of the mercury meniscus in AB. Look here, what they are telling. Note the reading of indicator tip. Here is your indicator tip. So by using the scale, you can measure the reading of the indicator tip. And they also ask you to measure the reading of the mercury meniscus in AB tube. This is the mercury meniscus. Also, you want to obtain the reading of the mercury meniscus used in the scale. Why we want to obtain these two readings? To obtain this height simple H. To obtain this height simple H. Comma, and the temperature of the water. And temperature of the water. By using this thermometer, you want to measure the temperature of the water. And the temperature of the water. Okay. Next point, write down. Heat the water slowly. Now, these points very important. Heat the water slowly. And thorough stirring and thorough stirring and thorough stirring and when the temperature of the water has increased, when the temperature of the water has increased by about 10 degrees Celsius, by about 10 degrees Celsius, comma, remove the burner, remove the burner, remove the burner, comma, stir will, stir will, stir will, and again arrange the tube AB, and again arrange the tube AB so that the mercury meniscus in CD, so that the mercury meniscus in CD, so that the mercury meniscus in CD touches the index tip, touches the index tip, touches the index tip, touches the index tip. Now, what they have said, what they have mentioned there, what they have mentioned there, please highlight some points. Heat the water slowly. Highlight heat the water slowly. Then highlight thorough stirring. Then highlight thorough stirring. Remove the burner. Remove the burner. Stir well. Remove the burner. Stir well. Stir well. Okay. So now, initially, now let's say, what are you doing? You are doing what now? We understand, you know, what we do in this practical, you have very clear idea. Changing the temperature, keeping the volume constant. You know how to keep the volume constant as well. And measuring the pressure. You know how to measure the pressure also. Pressure of the gas means pressure at point D. Pressure at point D means pressure at this point. Pressure at this point means H rho G plus phi. That's the idea. That's it. That's it. For different temperatures, you are obtaining the different corresponding pressure. Okay. But there is experimental methods to obtain those readings. Right? So you want to properly tell now, when you are heating the water, first thing is you should not open fully the burner. You should not open fully the burner. Right? So you want to open the burner slowly, and by using a low flame only, you want to heat the water. So why they are saying, now every point you write down, sometimes I don't give everything as a point also. Whenever you feel it's important, keep on writing. So why do we want to heat the water slowly? You should ask why we should heat the water slowly. Actually, this practical is all about measuring pressure at different temperatures of this gas. Our main primary concern is gas. Okay. But actually, we want to measure the temperature of the gas. Can we measure the temperature of the gas inside this bulb? We can't measure the temperature of the gas inside the bulb. Actually, we are measuring whose temperature? We are measuring temperature of the water. I want to measure the temperature of the gas inside the bulb, but I am measuring the temperature of the water. Is it okay? Actually, it's not okay. In order to say at least it's okay, you should heat the water slowly. Why? When you heat water slowly, then only all the liquid particles get enough time to get into same temperature. Then only water bulb and the gas inside the bulb obtains enough time to absorb the heat from the water and get heat into that temperature. Okay, that's why we should heat the water slowly. So then only we can ensure water particles, all the water particles. Okay, and also we want to stir it. We want to heat the water slowly, and also we want to stir it. Why we are stirring? Why do we want to stir it? When you stir it only, you can ensure all the particles, all the water particles has reached same temperature. Remember these points. Why we are doing stirring? Then only we can ensure all the liquid particles have obtained same temperature. Why we are heating slowly? Then only this gas, this bulb get enough time to obtain heat from the water and get heat into same temperature like water. If you maintain those conditions, stirring well, and if you heating the setup, then even though you measure the temperature of the water, we can say it's okay. Temperature of the gas is almost equal temperature of the water. Therefore, by measuring the temperature of the water, we can say that is the temperature of the gas also. Gas also. Gas also. Okay. Right. So now every time when you increase the temperature, now they are telling when you are taking reading, they are telling when you are taking a reading, first we want to what? Remove this Bunsen burner. Why? Now let's say now you are measuring, now your thermometer reading is earlier 10 degrees Celsius. Now temperature is 4 degrees Celsius. Now let's say now you want to measure the temperature, now you want to get the reading at 4 degrees Celsius. When temperature of the thermometer is around 38 degrees Celsius, you should start removing this burner. Because why? If the burner is still there, it keep on continuously increase the temperature of the water. Then you want to obtain readings at 40 degrees Celsius, but it temperature increases to 41, 40, 43. So therefore, remove the burner. When the temperature is around 38 something, then continuously stir it. Continuously stir it. Then what will happen? The temperature of the water automatically becomes 40 something. Okay, but you continue to stir it because already absorbed heat is there. It takes some time to propagate and it takes some time to what? Increase the temperature to 40. That is the idea. Okay, so every time when you increase the temperature of the gas, what will happen? Always this mercury meniscus tries to go down, tries to goes down. Always by moving this AB tube upwards, by moving AB tube upwards, you want to always keep your mercury meniscus at this indicator tip level. Then only you can ensure constant volume. Why we are doing? We can ensure constant volume of the gas. Okay. Right. Next point. Note the reading of the mercury meniscus in ABN. Note the reading of the mercury meniscus in AB. Note the reading of the mercury meniscus in AB. I think we wrote, okay, AB. Note the reading of the mercury meniscus in AB and temperature of the water. Temperature of the water. Temperature of the water. Okay. Right. Next point, write down. By increasing the temperature by about 10 degrees Celsius. By increasing the temperature, by increasing the temperature by about 10 degrees Celsius at a time until the water boils. At a time until the water boils. At a time until the water boils. Water boils. Comma. Calculate the difference in height level inside the bracket simple h. Calculate the difference in height level inside the bracket simple h, close the bracket, of the mercury levels in the two arms. 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 And draw the variation of simple h with capital T. And draw the variation of simple h with capital T. And draw the variation of simple h with capital T. Don't worry, I will explain. And draw the variation of simple h with capital T. Okay, now here what's happening. Now here what's happening. Okay. Okay. Look here. Look here. Okay. Now, right. Okay. 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 Right. So one last time, I will explain this one last time. We understand we want to maintain gas at different temperatures and we want to obtain corresponding pressure of the gas. That is the overall idea. But there are some steps to be followed when you try to maintain the gas at different temperatures. For an example, they are telling us to obtain readings by increase the temperature by 10 degrees Celsius, 10 degrees Celsius. For an example, let's say if you obtain readings of pressure and temperature when the temperature is at, for an example, 25 degrees Celsius, then heat the water and again get the readings when the temperature is 35 and again get the readings when the temperature is 45, 55, 65, 75, 85 until water boils. That means until 100 degrees Celsius. They are asking you to increase the temperature by 10 degrees Celsius, 10 degrees Celsius, and they are asking you to obtain the corresponding readings. Corresponding reading means pressure and corresponding temperature. Reading means pressure. Pressure means simple, it's something, and corresponding temperature. So then I told you that, let's say now you want to obtain pressure. You want to obtain pressure of the gas at 35 degrees Celsius. Now temperature of the thermometer is 33 degrees Celsius something. It's, if you provide heat, definitely temperature will be 34, 35. Sometimes it can exceed to 36 also. Therefore, what you have to do is, when the temperature of the thermometer is now, if you want to take the reading at 35 degrees Celsius, when you notice temperature of the thermometer reading is around 33 something, 33, 33.5 something, you should remove the burner. Right? Even though you remove the burner, already bottom part of the water is heated. Still that heat is not propagated to the thermometer. Still that heat is not propagated throughout the water. So therefore, when you continuously stir it, what will happen? That heat is also spreading throughout the water, spreading to the thermometer, spreading to the gas and the bulb. Automatically, temperature of the gas, temperature of the water, temperature of the thermometer reaches 34, 35 exactly. So you can control the temperature. I'm saying you can control the temperature at 35. That means if you remove the Bunsen burner exactly at 35 degrees Celsius, even though you remove it, due to the heat inside the water, temperature will become 36, 37. So different temperatures you are obtaining pressure. Now you know that we are measuring pressure. We are measuring pressure. What are the units to measure pressure? Pascal is 1 unit. If not, we can use mercury centimeter, mercury millimeter. What is this? Sometimes we can represent pressure as a length of a mercury liquid column. So you know that we can measure the pressure. We can measure the pressure as a length of a mercury liquid column. Okay. So then if I tell for an example, a pressure of this gas is, I can tell that 75 mercury millimeter. Mercury millimeter means it seems like a length. Mercury millimeter, when someone say mercury millimeter, it seems like a length, but actually this measures the pressure of this gas. It seems like a length, but it measures the pressure of the gas. If you want to convert mercury millimeters, if you want to convert mercury millimeters, if you want to convert mercury meters into Pascal, I taught you, you want to multiply by density of the mercury and gravitational acceleration. I told you, if you want to convert mercury meter into Pascal, you should multiply by density of mercury into gravitational acceleration. Now, so we know that from this ideal gas equation, we know that pressure PV equals nRT. If you maintain volume constant, pressure equals what? nR over capital V simple T. nR over capital V is a constant. R is a constant as the mass of the gas inside the tube, inside the bulb and the capillary tube is same. N is constant. As you are maintaining volume constant throughout the practical V constant, this entire term is a constant K. Then pressure equals KT. Pressure equals KT. So then what you can tell? Pressure. What is P mean? P means what? Pressure of the gas. We notice pressure of the gas means pressure at this point. If not pressure at this point. Pressure at this point. Right? Let's say atmospheric pressure is measured, this phi, the atmosphere rather than what is the atmospheric pressure? 10 to the power 5 Pascal. If not, tell me atmospheric pressure in mercury millimeter, 760 mercury millimeter. You can remember this idea. If this atmospheric pressure is measured in mercury millimeters or mercury centimeters or mercury meters, it is measured in mercury millimeters or centimeters or meters. Then if I ask you, what is the pressure at this point in terms of mercury millimeters? Just think simple H also measured in millimeters. Simple H also measured in millimeters. Mercury column only there. Right? This height, you can measure this length, simple H, you can measure it. Just think simple H is measured in millimeters. H means what? Mercury column height. Mercury column height, H is measured in millimeters. Atmospheric pressure is also measured in mercury millimeters. If I ask you to tell the pressure at this point in terms of mercury millimeter, what is the answer? So hands up who understand my question. Hands up who understand my question. I'm asking this idea. I'm saying this phi value. Okay, you want to reply in chat box also. Please reply in chat box. I'm saying atmospheric pressure is measured in mercury millimeters. Mercury as a column length of mercury. Phi is rather than measured in Pascal, it is measured in mercury millimeters. And this height also measured in mercury millimeters. I'm asking then, what is the pressure at this point? Reply everyone in the chat box. Reply everyone in the chat box. What is the pressure at this point in terms of these variables? In terms of phi and h, tell me someone, what is the pressure at this point? In terms of phi and h, someone tell me what is the pressure at that point? What is the pressure at that point? Could you reply? Could you reply? Phi plus h. Right, it is phi plus h. It is phi plus h. Right, you got it. This pressure phi plus h. If I ask you to convert into pascals, what you do? Phi plus h. If you want to convert into pascals, want to multiply by density of mercury into gravitational acceleration, that is kT. So you already know what is your independent variable. Independent variable. If not x-axis is temperature, your dependent variable. Your dependent variable. If not y-axis is, so when you change the temperature, this column height only change. So your dependent variable, if not y is simple h. So therefore, you want to subject simple h. When you subject simple h, what you obtain? When you subject simple h, understand, simple h will be k over rho g, capital T, phi plus h means kt over rho g minus phi. You're obtaining you're obtaining y equals mx minus c graph. This is y. This is the gradient. This is x minus c graph. So when you plot the graph, if you take 6 temperature readings, if you take 6 corresponding h values, your graph will be simple h measured in mercury something, and x-axis measured in kelvins, temperature measured in kelvins. Your graph will be y equals mx minus c. Y equals mx minus c. Obtain 6 readings, corresponding temperature, corresponding height, 6 readings. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is the practical. This is the practical. Genuinely hands up. If you understand this practical very clearly, hands up. Genuinely hands up. If you understand this practical, raise your hands. If you understand this practical, raise your hands quickly. If you understand this practical, raise your hands. Raise your hands. Raise your hands. Okay. So then I think when you refer it, you will understand it again. So then I explained, okay. Explain that idea, that graph also I explained. So this interception is what? Y equals mx minus c. This interception is equal to atmospheric pressure phi. Interception is phi. Therefore, this interception is phi. So we'll go with the discussion. We'll do the discussion. So next 2 practicals are not difficult like this. Remaining 2 practicals are easy. Okay. Discussion write down. Now I'm explaining everything. I want to explain everything also. Okay, what? Okay, write down. Okay, first point, write down. I can, okay, write down. First point, write down. First point. If not, rather than reading that, shall I share that photo? Then you can write it later. What is better? So give the point now. We will write it option 1. If not, okay, fine. Discussion. You explain the discussion. We'll write it later. Hands up who want to read the discussion and who want to write it now using, who want to write it now? So hands up who says, okay, you share the discussion, you take it as a photo and you share. So we'll write it later. So, but you discuss the points, we'll write it later, hands up. Okay. So I will send this. So, but I will explain. So you guys, what you do, you guys read and understand. I will share this. I will take a screenshot and I will share it. Give me a second. So I'll put in the main group. Okay. So tomorrow also we'll discuss at least 10 practicals tomorrow. Okay. Right. So first point, I will read it. First point, they are saying before each reading is taken. So now careful listen, okay. Before each reading is taken, tube AB suitably adjusted and the free mercury meniscus in tube CD is touched to the index tip. This assumes that the volume of gas trapped inside the bulb is constant. Because I told you why we always move this AB up and down and why we always ensure mercury meniscus in CD tube exactly at this tip level, to ensure constant mercury value, to obtain constant gas volume. That's what I mentioned there. This assumes that the volume of gas trapped inside the bulb is constant. Okay, first point is this assumes the volume of the gas trapped inside the bulb is constant, but the assumption is incorrect if the bulb expands. Right now, I told you we neglect when we carried out this practical, we neglect the expansion of the bulb. So if you don't think about the expansion, then we can always ensure volume of the gas inside the bulb is constant. But practically, when you increase the temperature, this bulb expands, right? So then this capillary tube also somewhat expands. Capillary tube expansion is not considerable when you compare with the bulb's expansion, but actually bulb is expanding. So then we can't consider, if you 100, if it is the real scenario, we can't consider volume of the gas inside the bulb is constant if you consider expansion. If you neglect the expansion, then we can tell that always, if you maintain mercury level the same indicator tip level, then we can tell volume of the gas in the bulb is same. That is the idea. Second point, they are telling capillary tube should be used as the connecting tube. Capillary tube should be used as the connecting tube to minimize the amount of gas that does not obtain the temperature of the gas inside the bulb. Now you know that this bulb is inside the water, but this capillary tube is not inside the water. How we heat the bulb? How we heat the gas inside the bulb? By using the water only, right? But we should understand the air in this capillary tube does not undergo to the temperature that we heat. We want to heat the gas inside the bulb. We want to heat the gas. We want to increase the temperature of the gas, but the gas in the capillary tube does not undergo that temperature. It's a problem, right? It's a problem. So when we do the practical, we are assuming all the gas obtain same temperature, but the gas inside the capillary tube does not obtain the same temperature like in the gas in the bulb. Then what is the solution? At least you should reduce the volume of the gas which does not obtain that temperature. Then how do you reduce the volume of the gas which does not obtain that temperature? By reducing the volume of the tube. That's why we are using capillary tube. So when you use capillary tube, we can say that very small volume of gas is inside the capillary tube when you compare with the bulb volume. Therefore, we can almost consider entire gas is at same temperature. Next, point number 3, they are saying, in order for the temperature of the gas in the bulb to equal the temperature of the liquid to be measured, it is essential that the heat be supplied slowly. I told you slowly, thorough stirring, and that the bulb be thin walled. These points they can ask. Okay, highlight slowly, thorough stirring, and bulb should be thin walled. Now I told you, actually we want to measure the temperature of the gas, but actually we are measuring the temperature of the water. Is it okay? Actually it's not okay, but we can say at least okay, it's okay. We can say it okay, then that's fine. When you continuously stir it, and when you supply heat slowly, and when this bulb is made with very thin material, because if this bulb is made with very thick material, difficult to propagate heat through the bulb. Then temperature outside the bulb and temperature inside the bulb are different. But if the bulb is made with very thin material, this heat is easily propagating from water to air without any resistance. Then if you maintain stirring and if you maintain slow heating, we can tell gas inside the bulb get enough time to heat to the temperature of the water. If you stir it, you can tell all the points have same temperature. If you provide heat slowly, gas inside the bulb get enough time to obtain the temperature of the water. If the bulb is made with thin material, heat is quickly transferring from water to air. Then we can tell they both gas temperature and water temperature are same. That says about point 3. Point 4, to ensure that the gas in the bulb has reached the temperature indicated by the to ensure that the gas in the bulb has reached the temperature indicated by the thermometer, comma, it is necessary to observe both that the thermometer reading is constant and that the height simple h is constant. Okay. Now what they are saying, to ensure that the gas in the bulb, to ensure that the gas in the bulb has reached the temperature indicated by the thermometer. In order to ensure the temperature of the bulb, temperature of the air and temperature of the gas and thermometer reading are same, to ensure whatever the reading shown in thermometer, same temperature is inside the bulb. To ensure that, they are telling two conditions must be there. First condition is reading. Thermometer reading should not vary with the time. When the moment you are taking reading, if you want to ensure the temperature of the gas is shown by thermometer reading, the thermometer reading should not vary. The thermometer reading should be constant. And also other side, you want to check this height also. If you notice at that temperature, if you notice this height is fluctuating, this height is varying, then understand temperature of the bulb is not reached the thermometer reading. That is the idea. That is the idea. Point number 5. Suppose readings are taken only during heating. Now when taking the final reading, since the height of H is large, the bulb AB has to be kept in a higher position. If the burner has been turned off and exits the lab within the AB tube in the same position, mercury may be drawn into the tube through the capillary tube as the system cools and the height decreases. To avoid this, care should be taken to keep AB tube in the lowest possible position when leaving the lab. Now, in that point, they are saying this idea. In that, they are saying, now what will happen? Now, when you keep on increasing the temperature, 30, 40, 50, 60, 70, 80, the corresponding H value also increasing, right? Corresponding H value increasing means you want to increase your AB tube to this level. Okay, right? So you want to increase your this, you want to keep this AB tube to this level. So then what you do, now, what you do, you off the Bunsen burner and you exit from the lab. Then what will happen? So when this bulb cools down, cools down, what will happen? Actually, they are saying the mercury in this AB tube can go through the capillary tube and can get into this bulb. Because of that high elevation, it creates high pressure to low pressure, that mercury propagates and mercury can get into this bulb. So to avoid that, they are saying after you doing the practical, remove the burner and everything and bring that mercury column also low elevation. Bring this AB tube also to a low elevation. Hands up who understand what I am saying there. Hands up who understand what I am explaining there. Hands up. Hands up who understand what I am explaining there. Hands up. Okay. So the last point is some time must be allowed for temperature of the air in the bulb to equal the temperature of the water. So the burner is periodically moved to and away from the heater. That's what I told you. Now, there should some time should be given. Some time should be given for the temperature of the air in the bulb equal to the temperature of the water. So some time should be given. Then you want to remove the Bunsen burner, and you should allow this water to. You should allow some time for this water to get heat and reach that certain temperature. Sometimes what we do, if you notice that your thermometer reading, even though you remove the burner and if you stir it continuously and if you note that still temperature of the water didn't reach that thermometer reading, then you can just little bit you can move this burn again for small time period. Again, you can remove it. Again, you can give small time period burning. Likewise, you can do it. You just read it and understand. So that is the practical. That is the practical. So we'll do 2015 structured essay question. So we can do it. So we can do it. So, but we'll do something like this. We'll discuss next two practicals. We'll discuss next two practicals and we'll do discussion. We'll do the structured essays. Okay. So genuinely hands up. Every point I discussed in here is very clear. Hands up. Genuinely you understand, hands up. If you really understand, hands up. If you really understand, hands up. Okay, hands up. Hands up. Now need a break. 9:45. We started at 8 30, 9:30, 9:45. Also, hands up, need a break, hands up. And today, what you do now, today itself, again, read the practical again. Again, do the question. So then, tar it once again. Okay, definitely you do that. Need a break now, hands up. So next to heat practicals, hereafter all the heat practicals not this much complex. This is somewhat complex. I also don't like this practical personally, this one. So we'll take a small break. We'll take around, now time is 9:45. So we'll take around 10 minute to less than 10-minute break. Just go and wash your face and come. Just go and wash your face and come. Right. Okay. We'll start. Uh, Practical number 24 done. We'll discuss 25 and 26. 25. 25. Okay. Right. Uh, so we'll do like this. Uh, okay, friend, that's fine. Okay. Right. 25. 25. That practical idea is not difficult. That is easy idea. Put your topic, practical number 25. Then we discussed 18 out of 38. Today we'll discuss now 18. Now we are discussing 19 practical, 19th one. Today somehow we'll discuss 20. 20 out of 38. 20 out of 38 practicals. Okay. Right. Put your topic, practical number 25, write down. Practical number 25, write down. Uh, Now in practical number 24, now you should understand what is this setup. You should understand this setup is the manometer setup to measure the pressure. To measure the pressure, this setup is used. Okay. This entire setup is used to measure the pressure. But when you look at your this practical book, rather than using this setup, they have connected a pressure regulator. Sorry, pressure regulator. They have connected pressure regulator. So you don't need to do all these things. You can directly measure the pressure from this regulator. So this setup is used for two purposes. One is to measure the pressure. Other one is to maintain constant volume. Right? The same thing is achieved here. If you just connect the pressure regulator by removing this entire setup. If you use a regulator, pressure regulator, you can read the pressure of the gas using the regulator indicated reading scale. Then what you can do now, this volume of the tube is constant, always constant, right? Therefore, better you learn this idea. It's a manometer setup. This is a pressure regulator. You know what is pressure regulator, right? Pressure regulator means device which we use to measure the reading of the pressure. So practical number 25, write down determination of the specific heat capacity. Determination of the specific heat capacity. Determination of the specific heat capacity of a solid substance. Of a solid substance. Of a solid substance. By the method of mixtures. 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 Okay. Now, so in this case also, so what you need, practical number 25, or not 24, 25. Practical number 25. Right. So what you need, materials and apparatus. You should need Nicholson heater. Now it's just, you can just write down as a heater, but better you write down Nicholson heater. Nicholson, it's a name, Nicholson heater. I will tell you what is Nicholson heater. You don't worry. Then write down two mercury thermometers. Two mercury thermometers. A calorimeter. A calorimeter. I will explain these things. Calorimeter. Then quantity of lead shots. Lead shots means small lead spears. Quantity of lead shots. Okay. Quantity of lead shots. A triple beam balance to measure the masses. Triple beam balance. Okay. So then you can use a tripod to heat it. Tripod wire gauge, right? Tripod wire gauge, something. Tripod wire gauge. Okay. So now I will tell you what's happening here. First of all, I will draw the diagram, but sometimes diagram seems like very complex, but overall process is very simple. Overall process is very simple. You guys also start drawing the diagram. You guys also start drawing the diagram with me. But don't you avoid drawing the diagram. I advise you to draw the diagram. Okay, I am advising you to draw the diagram. Okay, right. I will draw something here. So this is stir. So these are strings. Then what is this? This is the water, if not the whatever the liquid. So water normally. It can be liquid, any kind of liquid also. So this is we call as the calorimeter. Calorimeter means nothing but kind of a copper container. A kind of copper container. Right? Calorimeter. 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 Right? So this can be a wooden layer or something, wooden plate or wooden tray or something. Okay, I will tell you this. And this is the asbestos screen. Asbestos screen. I will tell you why we use each component. I will explain. Don't worry. But this heat practicals you can answer easily. You can answer heat practicals easily. అబ్బా. So I'm going to do something here. But actually, this is not that much relevant. This is relevant, but mainly you should focus this setup. This is the main setup, right? We are using this setup only to heat the lead shots. I will tell you, don't worry. It seems like a complex setup, but you don't fear about that. Only remember this setup. Okay. So now, if you want, you can draw your what? You can draw your stand. Then you can draw your Bunsen burner also if you want. If you want. Okay. Right. So now the story is actually very simple. The story is really very simple. It's not very complex. Okay, listen what the story. The story is, I will tell you what actually now this diagram setup seems like very complex, but not complex. Always understand what we should do. What are we going to do? If you understand those two, very clear. Setup is, you don't worry about the setup. Now, what is the topic? We want to find the specific heat capacity of solid. Uh, then we will discuss how to find the specific heat capacity of liquid as well. That means if they have given some set of, if they have given a solid material, you want to find the specific heat capacity of that solid material, right? So then, okay, so then you know what is specific heat capacity we learned. And also you know what is heat capacity C, and you know what is specific heat capacity S. You know the relationship between heat capacity and specific heat capacity C equals mx. Also we learned that, let's say now there's an object of mass simple limb. This object specific heat capacity is capital S. This object absorbs heat energy. The amount of heat energy absorbed by this object is, I say, capital Q. As a result, increase in temperature of this object is, I say, delta theta. We learn an equation. Amount of heat absorbed by the object equals ms delta theta. Ms delta theta. You guys can remember this equation. I hope all of you can remember this equation. Same thing, if this object releases capital Q amount of heat from the object, if you consider decrease in temperature is delta theta, if you want to find the amount of heat released from the object, that is also same equation, Q equals ms delta theta. That idea you should understand. Now in this practical, what I'm going to find is, I want to find the specific heat capacity of this lead shots. Lead shot means a small lead spears. I want to find the specific heat capacity of this lead. So this lead shots, if this lead mass is my object, I want to find the specific heat capacity of lead shots. Now here it is water, right? Only consider this lead shots. Here it is water. So just think this water is at the room temperature. This water is at 30 degrees Celsius. Okay, if I brief it, what we are, it seems like complex, but nothing complex. So there is a calorimeter. What is inside the calorimeter? Then temperature of the water inside the calorimeter is, I say, theta 1 for an example. So let's say now you are heating lead shots to a high temperature. You are heating lead shot. I consider one lead shot. Temperature of this lead shot is larger than the temperature of the water. I say temperature of the lead shot is theta 2. Temperature of the water is theta 1. Temperature of the water with the calorimeter, water with the container is theta 1. Then what would happen when you put this lead shot into the water? Who is going to release the heat? Lead shot releases heat. The same heat going to absorb by the water with the calorimeter. For your understanding, I consider specific heat capacity of lead shot S1, sorry, S2. And let's say specific heat capacity of water is S1. Just consider specific heat, just consider heat capacity, C. heat capacity of this calorimeter. This container is capital C. Okay. So then you know theta 2 is greater than theta 1. So what would happen when you put this heated lead shot into this water in the calorimeter? We know lead shot gonna release heat. That heat gonna absorb by the water and the calorimeter. Am I correct? So lead shot release heat. Lead shot release heat. That is gonna absorb by the. That is gonna absorb by the heat absorbed by whom? Heat absorbed by water plus calorimeter. Water plus calorimeter. Then how can I find the, let's say after this lead shot is put into the water, this lead shot is put into the water, somehow this system becomes thermal equilibrium. The last few days back I told you what is thermal equilibrium. Let's say the temperature of the now system after system became thermal equilibrium. Let's say temperature of the system is, I say theta something, theta. If I ask you, give me a relationship between theta 2, theta 1, which one is larger temperature? Temperature of the lead shot is larger, theta 2 is the largest, theta 1 is the smallest, theta should be in between theta 2 and theta 1. Am I correct? We know that. We explained theta 2 is largest, then theta, smallest theta 1. So then if I ask you to write an equation and give me an expression for the amount of heat released by the lead shot, mass of the lead shot, just take it as M2. Mass of the lead shot, just take it as M2. Then amount of heat released by the lead shot, M2, specific heat capacity of lead shot, S2, change in temperature. Initial temperature of the lead shot is theta 2, final temperature of the lead shot is theta, system have same temperature. Then M2, theta 2 minus theta must be equal to amount of heat absorbed by the water and the calorimeter. How do you find the amount of heat absorbed by the water? Mass of the water is, just take it as M1. Specific heat capacity of water is 1. Increase in temperature. Final temperature of the water is theta. Initial temperature is smaller theta 1. Theta minus theta 1. Plus, how do you find the amount of heat absorbed by the calorimeter? They have given heat capacity of calorimeter is C. Increase in temperature means initial temperature is theta 1, calorimeter's initial temperature theta, whatever the temperature of the water obtained by the calorimeter also. Why? They are in contact with each other. Initial temperature theta 1, now temperature is what? Theta. Theta is larger than theta 1. Therefore, theta minus theta 1. So you can take what? Theta minus theta 1 common factor and you can do something. We'll do it later. Actually, this is what we do. So what we are going to do is, we heat the lead shots. I will come to here, but as I want to brief what we are doing is practical only, I just did this one. We have set of lead shots, right? We are going to heat that lead shots to a certain temperature, to high temperature. Normally it's 100 degrees Celsius. Okay. So then what we do is, we are going to put that heated lead shots into the water at room temperature. And then we understand lead shots release heat, water absorbs heat, and they will come to an equilibrium temperature. So we are going to have an equation like this. And from this equation, we are going to find the specific heat capacity of lead shot. That is the practical. Then I will go in deep. Why do we need this setup? Why we need this one? Why we are hanging using strings, everything. I will explain deeply. Hands up who understand the brief. Hands up who understand the brief answer. Who understand the brief answer. So somehow today itself. Okay, now I will ask you one question now. Now we discuss 4 practicals today. Now, in practical number 12 and 13, from 2020 to 23, I discussed 3 structure essay questions, but there are 3 questions to be discussed. I didn't discuss. And practical number 14 and 15, there are also 6 practicals to be discussed. 2020 to 2023. 3 I discussed, 3 I didn't discuss. All together today, whatever the practicals we discussed so far, we have 6 practicals that we didn't discuss. Raise your hands out of you people. Hands up today, hands up who did those 6 structure disease hands up. Hands up who did those 6 structure disease questions also hands up. Today. So no one. So therefore, I would advise that better you do those 6 structured essay questions and better you review it today itself. If it is possible, please do them. If it is possible, do them. If it is possible, please do them. Okay, please do them. Okay, right. Okay. Right. Okay, now time is 10:20:23. Okay, so now okay, I will tell you. Okay, give me some time. Okay. Now okay. Now first what we do? First we take this calorie meter. Okay, what we are going to do first? First we take this calorie meter. First we take this calorie meter and we measure the mass of the calorie meter. Okay, the first step is take this calorie meter and keep that calorie meter on the scale, on the weighing scale or whatever, on the triple beam balance or whatever. Measure the mass of the calorie meter. Measure the mass of the calorie meter. Normally, that is our first step. That is our first step. Okay, sometimes what we do, we measure. Sometimes what we do, this is not important. Okay, not important. Not important. So first we do what? First measure the mass and measure the mass of the calorie meter. But normally what we do, we put the stirrer also in that empty calorie meter and okay, we put the stirrer also in that empty calorie meter and we measure the mass of the system. What is your system? Calorie meter and the stirrer. Keep in your mind. First measure the mass. Mass of what? Calorie meter plus stirrer. 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 So I put it as simple M1. I put it as this mass is simple M1. So then second step is, this is the idea. This is what we are going to do. Second step is, now put water, fill water with the calorie meter, but you should make you want to fill water to fill the calorie meter half. So please fill water up to half of the calorie meter. After you put the water, then what you do? Again measure the mass. This time you want to measure the mass of the calorie meter with the water. Calorie meter, stir is there. You are filling water, half of a calorie meter. Then you are measuring the mass. Then now mass means what? Now mass means calorie plus stir plus water. So take this reading, take this mass as simple M2. This mass as simple M2. Simple M2. Okay. Okay. Then why we use the setup? Forget about this setup. Now this setup, don't think anything. Now there is a Bunsen burner, there is a stand, and you see there is water inside this heater. This is some kind of heater. This Nicholson heater means it heats what? It heats water. There is water. This is water. So this heats water. Then what is here? And why there is a thermometer here? We understand these are lead shots. This thermometer is connected to the lead shots. And there is water. We are heating water. Okay. So why do we use this type of setup? This setup is used actually to heat the lead shots to the boiling point 100 degrees Celsius. So why we are using these lead shots? Why we are using this setup? To heat the lead shots to the boiling point, to the 100 degrees Celsius. How that possible? So when you keep on heating, what will happen? Temperature of the water increases. When the temperature of the water reaches 100 degrees Celsius, water starts boiling. When water starts boiling, water vapor, phase change happening, water vapor forming. When this water vapor contact with it's not direct contact. When this water vapor passes through this water vapor comes out to the surrounding like this. When this water vapor passes through this region, what will happen? The lead shot also obtains that temperature of the water vapor. Temperature of the water vapor is 100 degrees Celsius. These lead shots also obtain 100 degrees Celsius because of that water vapor. So you can ask that why we need this type of setup to heat the lead shots. Why don't we put these lead shots directly into this container, directly into this water? Because there is a problem. There is a problem. I will tell you that. I will tell you that later. Okay, I will tell this reason. The reason is okay. The reason is okay. I will tell the reason later. Okay. So why we use Nicholson heater? What is the primary goal of this setup? To heat the lead shots to the boiling point 100 degrees Celsius. But always we ensure these lead shots are not in contact with the water. So there is no any contact with the water, these lead shots. Right? What would happen if there is a contact with the water? Even though lead shots obtain 100 degrees Celsius, water droplets are placed on the surface of the lead shots. Right? So what will happen if you directly put these lead shots into the water, what will happen? Yes, lead shots become 100 degrees Celsius temperature. But the problem is when you are taking that lead shots and you have to put those lead shots into this calorimeter. But already you measured the mass of the calorimeter. Already you measured the mass of the calorimeter. You already measured the mass and water mass of the calorimeter. When you subtract these two, what mass you obtain? You obtain the mass of the water. So this is the mass of the calorimeter and stirrer. This is the mass of the calorimeter, stirrer, and water. When you subtract M2 minus M1 means mass of the water. What will happen when you rather than using setup, when you directly put these lead shots into the water, and when you heat the temperature of the lead shots to 100 degrees Celsius, when you are taking them, so those lead shots are wet with that water. Those lead shots are wet with those water. When you put that lead shots into the water, what will happen for the water mass? Because those lead shots are wet, along with that lead shot, some amount of water mass also get into this calorimeter. So therefore, you measure mass of the water as M2 minus M1, but actual mass of the water is something greater than M2 minus M1 because of the water coming along with the lead shots. So therefore, the best way is we should heat the lead shots. We should heat the lead shots without making them wet with the water. So that's why we heat them using this water vapor. This water vapor not in contact with the lead shots. So once these lead shots obtained 100 degrees Celsius, you can open these lead shots and you can allow these lead shots to pass through this path, and those lead shots get into the calorimeter. Then heated lead shots at 100 degrees Celsius. So it's not compulsory to make it 100 degrees Celsius. You can make it at 80 degrees Celsius or 70 or 60. It's up to you. After you heating those lead shots, when you open this cage, those lead shots pass along this path and they direct into this calorimeter. So once they mix with the water, the heated lead shots mix with the water at room temperature. lead shots emit heat. That heat absorbed by the water and the calorimeter. At a certain instant, they become thermal equilibrium. So then same story, same story, same story. Okay, same story. Right. So now then, so what we take as theta 1 temperature means now there's a thermometer. So you can measure the temperature of the lead shots. Using this thermometer, you can measure the temperature of the lead shots. What is theta 1? So theta 1, we can consider theta 1 as temperature of the heated lead shots. So I consider theta 1 as temperature of the heated lead shots. Temperature of the heated lead shots, that is theta 1. Okay. Temperature of, so you also write down these points. Temperature of heated lead shots, if not lead drops or whatever, lead shots. So this is theta 1. This is theta 1. Then what is my theta 2? My theta 2 will be initial temperature of the water, if not initial temperature of the calorimeter. Understand, water is in contact with the calorimeter. Whatever the temperature of the water is obtained by the calorimeter. So what is theta 1? What is theta 2? Theta 2 means initial temperature of water, if not calorimeter. Theta 2 means what? Theta 2 means what? Initial temperature of water, if not calorimeter, because both of them have same temperature. Calorimeter. So this is my theta 2. This is my theta. I put here theta 2. Okay, you can't see, I think. This is my theta 2. Theta 2. Theta 2. Then what is this theta 3? So what is this theta 3? Theta 3 means after these lead shots are in the calorimeter, that thermal equilibrium temperature, they come to a same temperature, right? That thermal equilibrium temperature is theta 3. Maximum temperature of the final maximum temperature of the mixture. So what is theta 3? Theta 3 means final maximum temperature of the mixture. So beta I erase this. Beta I erase this. Okay. So you understood this idea. Final maximum temperature of the mixture. Mixture means what? Stirrer, calorimeter, water, then lead shots. Final maximum temperature of mixture. So this is my theta 3. Now very easy story now. This is my theta 3, very easy story. Then sixth one. What is sixth one? Mass of the mixture. Sixth one, mass of the calorimeter with the mixture. Sixth one is what? Mass of the calorimeter with the mixture. If not mass of the calorimeter with the lead shots, whatever. Mass of the calorimeter with mixture or with lead shots or whatever, with lead shots. With lead shots, that is my M3. That is my M3. So if I draw this this time, stirrer, calorimeter, then water, also lead shots, also lead shots, also lead shots. This is the mixture mass. Okay, after you obtaining this, then you can easily find the answer, right? So then those are the readings. So just consider specific heat capacity of, then we'll consider like this. Then we'll consider like this. Specific heat capacity will consider then specific heat capacity of calorimeter material, specific heat capacity of calorimeter material, specific heat capacity of calorimeter material, calorimeter, we'll consider it as what? We'll consider it as S1. Then specific heat capacity of water, we'll take it as heat capacity of water, we'll take it as SW. And what I want to find specific heat capacity of copper lead, lead shots, right? Specific heat capacity of lead shots, we'll take it as capital S. I want to find capital S. I want to find capital X. Okay. Right. Up to now, everything is very clear, hands. Up to now, everything is very clear, hands. Up to now, if everything is very clear, hands. Up to now, if everything is very clear, hands. Okay. Right. So now we'll go with an assumption. Now, when these lead shots are immersed in this water, if there is no heat transfer to the surrounding, assume no heat transfer to the surrounding. No heat transfer to the surrounding, to the environment, to the surrounding, okay, surrounding. Then what you can tell? The heat emitted by the lead shots must be equal to heat absorbed by the calorimeter and water. So we can write down heat emitted by the lead shots. Heat emitted by lead shots must be equal to heat absorbed by water and calorimeter. Heat absorbed by water and calorimeter. So then quickly write on the equation. Then if you write the equation properly, I write here. Huh? So I have no space, I write here. Someone tell me, how do you find the heat emitted by the lead shots? M is delta theta. Can you tell how to find the mass of the lead shots? Reply in chat box, how do you find the mass of the lead shots? By using these variables, someone reply the chat box, how to find the mass of the lead shot. How do we find the mass of the lead shots? Reply. How do we find the mass of the lead shots? Reply. How do we find the mass of the lead shots? Reply someone quickly. Chat box. How do you find the mass of the lead shots? Reply someone quickly. Mass of the lead shots. Reply quickly. So we can find, see, now, so this is the mass. M2 means mass of stirrer, calorimeter, water. M3 means mass of stirrer, calorimeter, water, lead shots. Then when you subtract M3 minus M2, that is the mass of the lead shots. So you can tell M3 minus M2. Okay, see, M3 minus M2, mass of the lead shots, into M is delta theta, right? S means specific heat capacity of lead shots. Specific heat capacity of lead shot, that is capital S. That's what I want to find. This is what I want to find. Okay, by using triple balance, you can measure the mass. By using thermometers, you can measure. You are putting a thermometer here also. You are putting a thermometer here also. There's a thermometer here also. There's a thermometer here also. Thermometer, okay, right? So then, heat released by the lead shots, mass the lead shots into specific heat capacity of lead shot into when you put lead shot into the water, what will happen with the temperature of the lead shot? Temperature of the lead shot decreases. Then initial temperature of the lead shot is larger, theta 1. What is the initial temperature of the lead shot? Initial temperature of the lead shot is what? Theta 1. What is the final temperature of the lead shot? Theta 3. Final temperature theta 3. What is the change in temperature? Initial temperature is larger, theta 1 minus theta 3. So this is the amount of heat released by the lead shots. So who gonna absorb that heat? That heat gonna absorb by the calorimeter and water. So we'll find the amount of heat absorbed by the water. What is the mass of the water? Mass of the water. Stir a calorimeter, water. Mass of the water is M2 minus M1. M2 minus M1. What is the specific heat capacity of water? SW, we know 4200. What is the change in temperature of the water? Initially, water is at room temperature. Initially, water is at room temperature, theta 2. But now what happened after putting lead shots? Temperature of the water is increasing. Now temperature of the water is theta 3. Then change in temperature of the water is how much? Theta 3 minus theta 2. So this is the amount of heat absorbed by the water. Plus calorimeter also absorbing heat. What is the mass of the calorimeter? With the stirrer, M1. Mass of the calorimeter with the stirrer is M1. Specific heat capacity of calorimeter? Specific heat capacity of calorimeter, S1. What is the increase in temperature of calorimeter? Initial temperature of the calorimeter is theta 2. Final temperature is theta 3. Theta 3 minus theta 3. Theta 3 minus theta 3 minus theta 2. This is the equation. So what you can do here you can take theta 3 minus theta 2, theta 3 minus theta 2 as your common factor. If you take it as common factor, you can write down M2 minus M1 SW plus, so you can't see, right? So you can write down, okay, M2 minus M1 SW plus M1 is 1, M1 is 1, theta 3 minus theta 2 equal to this. Hands up, everything is very clear. That's it. Hands up, everything is very clear. Hands up. Hands up, everything is very clear. Hands up. Everything is very clear. Hands up. Everything is very clear. Everything is very clear. Okay. So everything is very clear now. So now this is the idea. This is the idea. This is the idea. Okay, give me some time. Give me some time. Okay, give me some time. Okay, then again, what I do, method and discussion, I will share a small screenshot. You also read that. So we'll go to the discussion. We will go to the discussion also. Okay, we'll go to the discussion. I will share a screenshot. Give me a second. So you revise the practical book also, but whatever the things I give is not 100% practical book things. Okay, discussion everything are not in the practical book, but it's okay to refer. Method is almost similar to practical book note, but not always. Right. Okay. Now we'll discuss them. So when you refer that images, okay, what they are saying, we'll go back what they are saying. Uh, they are saying they are telling topic. It is mentioned as finding the specific heat capacity of a solid. This time, lead shots are our solid. Okay. Now, number one, measure the mass of the empty calorimeter and stirrer, and measure the mass M2 of the calorimeter. Fill with the water about half full of the calorimeter. Yes, we discussed. Second point, heat the water in the heater by placing the lead shots, which have been found to be completely covered by water into the Nicholson heater, and adjust the bulb of the thermometer so that it touches the lead bullets. It touches the lead shots. So they are telling that heat the lead shots using this setup. But when you place thermometer, please always keep your thermometer in contact with the lead shots. Thermometer should be placed in contact with the lead shots. That's what they are telling. So third point, they are saying, after the temperature reaches a constant value, note that value theta 1. Place the calorimeter under the heater's outlet and note the initial temperature of the water of the calorimeter theta 2. Lift the lift that what cage something. Lift that cage of the heater and let the lead shots to fall into the calorimeter. Obtain final maximum temperature. Always highlight when you are writing also. So you want to find finally this theta 3 means understand. Theta 3 means understand final maximum temperature. Highlight these two terms should be there. Final should be there. Maximum should be there. Final maximum temperature. Because why? So when you add this lead shot into the mixture, what will happen? Temperature. What will happen? Temperature now. When I measure the thermometer, when I measure the temperature using thermometer reading increases and start decreasing. So you want to measure theta 3 as the final maximum temperature. Final maximum temperature. Uh, Measure the mass of the calorimeter with lead shots M3. Assuming no heat exchange with the environment, then heat emitted by the lead shots must be equal to heat absorbed by the calorimeter with the water. Then finding the specific heat capacity of a liquid. Now here, what have we done? Here we found specific heat capacity of solid lead shots. Now, if you want to find the specific heat capacity of liquid, if you want to find specific heat capacity of a certain liquid, what you should do? Okay, nothing different. Now here, what have we done? Here we used lead shots, lead shots. Here we used water, water. If you want to find the specific heat capacity of certain liquid, if you want to find the specific heat capacity of certain liquid, put that liquid instead of water. Put that liquid instead of water. And you should have a kind of solid something. It can be lead shots also. You should have kind of solid something, but you should you should know the specific heat capacity of that solid. Same story. Instead of water, replace water by the liquid that you want to measure the specific heat capacity. Then use a known object, use a known solid, use the solid, you use the solid which you know the specific heat capacity. So then put that into this liquid and follow the same thing. Follow the same thing. So not that much difficult, that story. So they are saying there specific heat capacity of a liquid can be found as in the above experiment by using a liquid whose specific heat capacity to be found instead of water. I told you, and a solid substance whose specific heat capacity is known instead of lead shots. That's the story. Discussion. Discussion is important. Discussion is important. Now, first point they are saying. First point they are saying. Nicholson heater is useful for heating lead shots to a known temperature without contact with the water. I already told you, right? So we use this Nicholson heater to heat the lead shots without we use this Nicholson heater to heat the lead shots to a certain temperature without contact with the water. Why? And for transferring the lead shots to the calorimeter with minimum heat loss. Minimum heat loss. Now, what will happen now? Now think practically rather than using this setup. Now here what you do? So you heat the lead shots by using Nicholson heater. When you open the cage, they go through this path and they fall into the water. So the time taken for the heat loss from here to here, heat loss from the moment you release the cage and the heat loss from the moment you release the cage and when it falls into the water, that heat loss is very small. But what if you put the lead shots into the water and then you want to collect those lead shots, you want to collect those heated lead shots, and you want to put into the water? Then what will happen? Then it takes some kind of considerable time. In that time, what will happen? The temperature of the lead shot is changing. The temperature of the lead shot is reducing. Okay, so that is what they mentioned in the first point. Second point, when the lead shots are being transferred to the calorimeter, care should be taken to prevent splashing out of the water in it, because sometimes you know that when these lead shots quickly fall into the water, this water can splash. When this water splashes, what will happen? Already we found the mass of the water. When this water splashes out, actual mass of the water is lesser than the what? The mass that we take as the water mass. If it is splashing when you put lead shots, actual water mass is less than the what? Readings of the mass of the water. You understand, right? So the mass that you use for the calculation and actual mass of the water is different. So therefore, you want to very carefully, slowly, you want to allow lead shots to fall into the water. That is the idea. So that is the idea. That is the idea. So because the measurements related to mass of water have now already taken, because it can be an inaccurate situation. Next one, observe the thermometer reading very carefully. Observe the thermometer reading very carefully. Since lead shot is a good conductor, the mixture reaches the maximum temperature very soon. Okay, the mixture reaches the temperature very soon. Okay, now after you put lead shot into the water, because these lead shots are good conductors, therefore they transfer heat to the water and quickly temperature of the thermometer increases. So therefore very carefully observe when you obtain the final maximum reading. If you just miss it, sometimes it reaches final maximum temperature and it might come down. So when you look back, that temperature shown is not the maximum temperature. I think you understand. Okay, you understand. Our time is 11. Shall we take a small break and come? So now I won't discuss few more points actually. I will discuss few more points. We'll take a small break and come. So we'll take a small break and come. So time is 11 o'clock. We'll take a small break and we'll discuss one more practical and we'll go home. So I will give again 10-minute break. Okay. Small break and come. I will discuss these points again. We'll take a small break and come. Now you can do all the practicals. Okay. Now all the practical structure is you can do it. Do now. You do now. Just allocate now. Physics time, allocate it and somehow manage it and do now. Okay. Okay. Give me to take 10 minutes, 10:57. I will come at 11:07 no 11:10 something. Can someone reply at what time I give the break? Or 11:10. Can someone reply at what time I give the break? Can someone reply at what time I give the break? No replies. 10:58. 11:10. Uh, uh, shall we have another 5 minute break? Is it okay? Hands up. We'll take another 5 minute break. Hands up. We'll take another 5 minute break. Hands up. Okay, we'll take another 5 minutes. Okay, 5 or 6 minutes.
Right. I'm back. Okay. So what was the last point that you were discussing? The last point that we were discussing. Okay. Now, point number 3, observe the thermometer reading very carefully since lead is good conductor. The mixtures reaches the maximum temperature very soon. I explained that point. Point number 4, the following measures are taken to minimize the heat loss to the environment from the hot calorimeter. Now we derive this equation under a main assumption there is no heat transfer to the surrounding. But actually, there is a heat transfer to the surrounding. Heat transfer to the surrounding in different methods. Heat transfers through conduction, heat transfer to the surrounding through convection, heat transfers to the surrounding through radiation, heat transfer to the surrounding through evaporation also. So now, when you are carrying this practical, you want to ensure you can't completely avoid heat transfer to the surrounding, but you should ensure minimal heat transfer to the surrounding. Then only we can consider all the heat supplied by the lead shot only given to the water and the calorimeter. So you should avoid heat transfer to the surrounding as much as possible. So then what are the steps that you take for this? So how do you reduce heat transfer to the conduction, heat transfer through the conduction? Because we know that there are three main ways of heat propagation: conduction, convection, and radiation. Conduction means the heat transfer through solid surfaces, solids. Convection means heat transfer through fluids. Fluid means liquids and gases. What is radiation? Even though there is no medium also, it's possible to transfer heat as radiation, like how sun radiation comes to the earth. Okay. Now, fourth point they are telling, following measures are taken to minimize the heat loss to the environment from the hot calorimeter. Number one, to minimize the heat loss by conduction, the calorimeter is suspended by a string in an external container so that it does not touch any solid material. Now, this calorimeter is heated. So we should avoid heat transfer to the surrounding as much as possible. So what would happen when you keep this calorimeter on another solid surface? Heat can transfer from calorimeter to the solid surface. So therefore, to avoid that, what we do, we hang this heated calorimeter. We hang this heated calorimeter to another container using strings. Now, what would happen if you don't use the strings and if you just keep the container on this one? Heat transfer happens from the calorimeter to the container through conduction. But if you hang using strings like this, so the heat transfer through conduction is minimum. So then next point is to minimize heat loss by convection. Calorimeter is insulated with a material such as wood dust, regiform, or asbestos fibers. Now sometimes due to the temperature of the calorimeter, if calorimeter is surrounded by air is a fluid, then what would happen? This heat there can be a heat loss if not the heat of the calorimeter transfers to the air as what? Convection. Then heat can dissipate as convection. To avoid heat transfer through convection, what you do, this gap you fill with regiform. If not this gap you fill with wooden chips. This gap you fill with asbestos fibers. Then you can avoid heat loss as convection. Next one is radiation. Radiation, now they are telling point number 3, the surface of the calorimeter is polished. The surface of the calorimeter is polished to minimize the heat loss from radiation. To minimize the heat loss from radiation, that surface. So what will happen if, understand, if the surface of the calorimeter is polished, well polished, we can reduce heat loss as radiation also. Keep that in your mind. Next one is, we know that any temperature, now no matter this water is at any temperature, what will happen? due to the temperature, some amount of water will be evaporates. Some amount of water will be evaporates, right? So then, if that water evaporates also, along with that water vapor, heat is passing to the environment. To prevent that, we are using kind of lid. So if you cover this calorimeter using a lid, no water vapor is evaporating into the surrounding. So then you can reduce the heat loss. You can reduce the heat loss. That is the idea. That is the idea. Okay. Fifth point. Now, fourth point, the calorimeter is covered with a lid to minimize the heat loss from evaporation. Next point is the calorimeter should only be brought near the Nicholson heater for short time needed to exchange the leads. Even then, an insulating plate is placed between them to prevent the heat of the hot Nicholson heater from reaching the calorimeter during the short time. Now you know that. So now we are heating this lead shots using Nicholson heater. So this region is very heated region. So from the beginning itself, if you keep your this calorimeter closer to the Nicholson heater, the heat, so this heat will transmit to the calorimeter and what will happen? Calorimeter get heated. It's not desirable result. So therefore, always you want to know. So you should bring this setup. You should bring this setup when these lead shots are ready to release. When these lead shots are sufficiently heated, even when these lead shots are reached that desired temperature, when these lead shots are heated, and when these shots are almost ready to leave, then only you want to bring the setup towards the Nicholson heater. Even that small time period, lead shots are transmitting to the calorimeter, you should maintain kind of asbestos layer to avoid heat transferring from Nicholson heater to calorimeter. This is that asbestos layer. Okay, so you are placing the system also on kind of wooden layer also. Okay, that is that point. That is that point. Then what? So then the method of compensation. Okay, method of compensation can be used as a remedy for the loss of heat. Okay, the initial temperature of the calorimeter with water first cooled by 5 degrees Celsius before the mixing. The heated substance is then added to the water and mixed well so that the temperature of the mixture rises by 5 degrees Celsius above the initial temperature. The heat gained by the mixture during 5 degrees Celsius below the initial temperature is expected to compensate with the heat loss by mixture during 5 degrees Celsius above the initial temperature. Okay. Now, now, so now this practical will be accurate when there is no any heat loss. But it's not easy to do this practical without any heat loss. It's not possible. So we have taken, even though we have taken all the necessary steps to avoid, if not to minimize the heat dissipation to the surrounding, but still some amount of heat dissipate to the surrounding. So what we do for this case, so we can go for a method. That method we are calling as, better you highlight also when you are writing the note. That method is we are calling as method of compensation. Highlight that word many times they have asked in the exam also. Method of compensation. So what is the idea? What is the method of compensation? I will erase this entire thing. I will erase this. I will erase this. I will erase this. Okay. And please someone tell me the past paper question years regarding this practical. Past paper years, someone tell me regarding this practical. Okay. Okay. Now I will tell you what is heat of compensation. So this is right heat of what is this? It is called as method of compensation. Okay.
So we'll discuss this also. Method of compensation. Method of compensation. Now I will tell you the idea. Now what we do here is, now this is your calorimeter. Now actually I discussed initial temperature of the calorimeter is the room temperature. The room temperature. But if you are going with the method of compensation, what you do, very careful listen, what you do, you reduce the temperature. Very careful understand. What you do, you reduce the temperature of the calorimeter 5 Celsius less than the room temperature. That means you start beginning the practical, you start the practical, then you start the practical initially reducing the temperature of the calorimeter by 5 degrees Celsius than the surrounding temperature. Let's say your atmospheric temperature, your room temperature is 30 degrees Celsius. By adding some ice cubes, using the thermometer, by adding some ice cubes, what you do, you reduce the temperature of the calorimeter with the water 5 Celsius less than the room temperature. If your room temperature is 30, temperature of your calorimeter is 25 degrees Celsius. Okay, right. So then what you do, you keep on adding. Now the initial temperature of the calorimeter with the water is 25 degrees Celsius. Room temperature is 30. Now you keep on adding lead shots. Until the temperature of the calorimeter now 5 Celsius greater than the room temperature. Now room temperature 30 degrees Celsius. You start doing the practical from 25 degrees Celsius. That means theta 2 is 25 degrees Celsius. Room temperature is 30. You add lead shots. Until temperature of the mixture becomes 5 degrees Celsius greater than the room temperature. That means finally, final temperature of the system should be 35 degrees Celsius. Then this is what we call as method of compensation. Why it's compensation? Now what would happen? Initially setup was at 30 degrees Celsius. By adding ice cubes, when you reduce the temperature 25 degrees Celsius, actually what's happening? Heat is emitting from the calorimeter. Am I correct? Initially, your calorimeter with water is having 30 degrees Celsius only. When you reduce to 25 degrees Celsius, what will happen? Heat is, what will happen? So when you reduce, okay, my bad. Okay, when you reduce the temperature, what will happen? Initially, it is 30. By using ice cubes, if you reduce the temperature, what will happen? Heat will be what? Ice cubes, what will happen? Heat is emitting, right? So when we decrease the temperature, yes, heat is emitted, okay. Right, when you decrease the temperature, heat is emitted from the calorimeter. Okay, let's say, so where initially calorimeter with the water temperature is 30 degrees Celsius, when you reduce to 25 degrees Celsius. When you reduce to 25 degrees Celsius, what will happen? Heat is released to the surrounding. So that heat is, I say, Q. So then you are adding what? Then you are adding lead shots. So when you are adding lead shots, now what will happen? Now temperature. Now what will happen? Now temperature of the calorimeter is increasing. That means what will happen now then? Now heat is absorbed in the surrounding. Heat is absorbing to the calorimeter from surrounding. So then what will happen? Whatever the heat released, then the heat absorbed are same. So therefore we can tell there is no overall heat transfer.
Hands up who understands this idea, hands up. Hands up who understands what I'm explaining, hands up. So when you reduce the temperature less than 5 degrees Celsius than the room temperature, and when you when you maintain your final temperature 5 degrees Celsius greater than room temperature, what will happen? The amount of released heat to the surrounding and amount of absorbed heat to the from the surrounding becomes equal, and there is no any overall heat transfer. There is no any overall heat transfer. So that is the idea. This is what we call as method of compensation. If you do something like this, we can ensure there is no any heat transfer to the surrounding. But there's a problem. There's a problem. What is the problem? Now we can't, now when you keep on adding lead shots, we can't maintain. Now if you want to do this, your final temperature, final maximum temperature must be 35 degrees Celsius. You want to maintain always final maximum temperature 35 degrees Celsius. But when you keep on adding the lead shots, we can't control the final temperature, right? Even though we want to maintain 35 degrees Celsius, how do we know how we can add lead shots to maintain 35 degrees Celsius? Sometimes the final temperature can exceed 35 degrees Celsius. So therefore, this is also practically somewhat difficult. Why? Because we can't control final temperature of the system because of these lead shots. So that is that idea. So these are the important points. Can someone share? Today we could discuss only 5 practicals. Actually, I plan to discuss 10 practicals. I plan to discuss 10 practicals. I don't know what I'm okay. I plan to 10 practicals, but could discuss 5 practicals only today. Then altogether, we have discussed only 19 out of 38. That means 50% practical we finished, 50% is there. But I will tell you these things. Now, the last practicals from electronics, everything, they don't ask. They don't ask, but have to do. So I will prioritize this heat practical. Then I will prioritize this unit 3 oscillation and waves practical. So then viscosity, surface tension practicals I will prioritize. That electronic practicals, they don't ask actually. They have never asked. They have never asked. I'm not justifying. Plan to do 10 practicals. Now time is already 11:33. Someone please share the past paper years also. 11:33. Now hands up who feels this is effective for you. This is effective, hands up. Hands up who feels effective, hands up. So I am without skipping everything I am explaining. I don't know. I'm not skipping anything. Now I think that if you, I don't know why students don't come to the session, but I don't know actually. But but only this tomorrow. Tomorrow is the only holiday. Somehow I want to finish remaining 19. Remaining 19 I want to finish tomorrow and Saturday, Sunday. Right? Saturday, Sunday. I will do it. Somehow I will do it. I have to do it, right? So I will do it, but this is the way. I don't know. I don't know. Okay, I'm doing. So what you do now? So we have 3 essay questions: 2002, 2007, 2011. 2002, 2007, 2011. So you guys try doing these 3 structure essay questions. Okay, I will give a small homework also before you sleep. If you didn't do that 6 structure essay questions, do them. And do this 2002, 2007, 2011, and also do 2015 structure essay question. But sometimes you might face bit difficulty when you are doing 2015 structure essay question. It's not because of the practical, it's because of that year paper. That year paper is so much difficult. So even the structure essay question is also difficult. Therefore, you try 2015 also. Tomorrow I will ask how many of you did these practicals again, did these structure essay questions again, according to my request. So therefore, so tomorrow also I'm doing, not morning. I'm preparing. I'm preparing. I'm preparing. This is the first time I'm teaching practicals. Okay. This is the first time actually. I never have taught practicals for any batch before. He didn't do it. I somehow want to finish it, but I'm not in a hurry. Still I'm not in a hurry. But explaining all the points. So I can guarantee explain all the points. So you calmly you join, because you don't avoid coming these days, because you know these practicals very important. Definitely you can score 20 marks. Definitely one practical comes from that resonance something. One practical comes from heat, one practical from electricity something. I don't do electricity practicals already, I discussed everything. So therefore you can grab 15-20 marks quickly. So therefore don't skip it and come. Don't skip it and come. Now don't you think about exams. Now already you have worked harder. You have worked harder. Now this we have 1 week to go. I think today, now what the date is. Now I will talk little bit 2 5 minutes and I will stop. If you feel the time waste, you can leave also, it's okay. So I will tell the story. Now we have 15, 25, we have exam 25, it's Monday. Today 14. So 15, 16, 17, 18. So let's say 18 is this Monday, 25 you have exam. So you have around 10 days. So you have around 10 days. Now even you study from morning to late night, even as we have around 10 days, even you study early in the morning to late night, there is actually no use. I don't tell not to study, as we are spending last 10 days. Even you study early in the morning, late night, there is no use, because the knowledge, the experience that you take to do a paper, you should have already obtained within that last 2 years you spent. Okay. Normally, I advise you to, yes, do only questions, do only questions. And now I don't advise you to refer the notes. I don't advise you to refer the notes, but I advise you to don't waste your time referring notes, but I advise you to refer the short notes. So do only the questions, don't do any. uh, if you covered all the past paper years, if you fully confident with past papers, then okay, then you just try some model papers, there is no doubt. I am telling for the students who didn't even cover past paper questions fully, prioritize past paper questions as much as possible. Past paper questions as much as possible. And as it is last 10 days, I am telling you, no need to, don't you wake up until 12 1 and don't you study, no use. So don't do that, right? So if you should have studied last month like that, you should have studied 2 months before like that. So don't you do that. Be very calm, be very calm. This is just an exam only. This is an exam only. You have done something better for last 2 years. This 10 days, what will happen? I will tell you. 10 days, if you now these students now they are very fear and they are losing their confidence. Most of them now they don't even feel to study. So now most of them already they are planning to second shy. Some of you plan to skip first shy. Okay, I'm going to skip first shy. I will do it better in second shy. So these are very common issues that every year students face, right? So the thing is, it's obvious when 10 days in front of exams, if you have 10 days and you have exams in front, then we are not mentally stable. Even though a student who studied hard is a bright student, even for that student also, same feeling. So even he is a very bad student, he still don't have confidence that whether he get 3 A's or not. So this is very common. So I tell you one thing. Now, these 10 days, you should have a good sleep. Now I advise don't you sleep 2 hours, 3 hours. Now sleep, because now sleep at least 6 hours. Sleep 6 hours. And what you do now, if you have a day, if now you have full days, if you have full days, divide into your full day, divide into three parts. Full day divided into three parts. What you do, allocate each part to each lesson: physics, chemistry, combined maths. Okay. So in that time period, mainly you refer the short notes as much as possible while doing the questions. While doing the questions, refer the short note as much as possible, right? So now you don't need to keep time and don't you do the SAO structure to MCQ questions, but randomly select, and do it. It's better if you want to revise the sections, go with section wise MCQs. You take it and do that, but don't take so much of time. Quickly do it. Don't, if you don't know something, don't take note and don't you start referring from the beginning. But if you have short note, that's why already I told, I really want to bring that practice from the beginning itself. That's why initially I short note thing and past paper thing, everything I started. If you have followed properly, you don't want to fear that much. Only this practical is problem. I know this practical is a problem. I know that that is a problem. So therefore, give priority for short note revision. If you have made that small book I told you when we were doing papers and everything, I ask you to write all the important points. Likewise, if you maintain something, refer that. Wherever you go, just refer that. Okay, then sleep well, because now these days what will happen because of the high stress. What you guys do, sometimes you get headache, head is paining, then you guys get what, stress, you guys get what, different diseases, illness. So therefore, then automatically now, if you are facing a kind of disease or sickness or illness, then definitely when you face your exam also, you don't want to face the exam with your best. So therefore, so don't allow any disease to catch you in these days. Always keep calm. What will happen? Nothing will happen. Always think that what will happen is a shit. Nothing will happen. Yes, I tried my best. Okay, I'm doing what's my possible. I'm just trying how much I can score. I'm going to try how much I can score in first shy. That's it. That's it. So if you start thinking what will happen now, whether I will get A or not, whether I will get B, or God, if I get B, what will happen for my dream? What will happen for this? Everyone look at me, everyone laugh at me. Oh God, I can't do this. I am going to fail. Automatically you lose your confidence and automatically you don't perform with your maximum. So why we should think like that? So therefore, normally it doesn't matter. Okay, I studied whatever my best and I am going to face the exams and I am going to do that. Always keep that in your mind. So these days, even you put big effort, even though you put big effort now, if you miss lots of things, even you put big effort, and if you cover it also, nothing gonna happen. I told you, uh, plan, plan. That means plan means always don't focus to cover everything. Whatever sections that you are thorough more. Because if you want to get A, you should be very tactic now. Matter and radiation. Likewise, select some lessons. So then prepare for that. So likewise, be tactic and do it. So that is what I want to tell mainly. I don't want to waste your time. Practical, practical. Do what I say today before you sleep. Today work before you sleep. That's six structured and these three structured, all the nine structured. Just do look at the answers if you don't know, and also refer what I explained also. Refer what I explained also. I explained all the points without skipping. Then do it. So only 19 practical done today. Another 19 to be done. Another 19 understand around 10. We don't want the last few. We don't want actually, but I am prioritizing remaining heat practicals and optics some practical. So tomorrow I plan to do 10. Tomorrow plan to discuss at least 10. I don't know whether I can. So Saturday also I am doing. Sunday also I am doing. Somehow I want to discuss it. 19, that is must. Okay. So other than that, all the main theory parts I taught you. All the main theory parts I taught you. Still this logic gate part is there. Somehow Sunday I will do it. I don't know whether you come or not. I don't know, but I will do it. Right? I will do it. Small part is there. Thermometer. That's it. Okay. I will do it somehow. Okay. Okay. You guys can go home, have fun. I'm stopping from to here. We'll meet another day.